Hi everyone and welcome back. It's Kira Garfolo with Math 109 at Greenville Tech. Today we're going to be talking about the fundamental theorem of algebra, which is section 6.4 in our book. This is a really important section for those of you that will continue on to calculus, as the fundamental theorem of algebra continues to show up in later math. The fundamental theorem of algebra just tells us that for any function f of x, if it's a polynomial function of a degree greater than or equal to 1, so linear function or higher, then f has to have at least one complex zero. That's pretty mathy, I know. So what does this actually mean in plain English? Well, it means for any polynomial function, we can find at least one root. But it doesn't necessarily tell us that the root has to be real. The roots may be complex, or you may have a combination of real roots and complex roots. They may all be complex or they may all be real. Remember that complex means that we have a real and an imaginary component to the number. So really any number could be written as complex. It could be entirely the real portion, entirely the imaginary portion, or a combination of both. But remember that a complex number can be written as the real part plus or minus b, that imaginary part, times I. The I is what makes it imaginary. Remember that I is the square root of -1. When we look at a graph, remember that our roots are our x-intercepts, but only the real numbers are going to show up as x-intercepts because we can only graph a real number, right? So back to the fundamental theorem of algebra, more specifically, we know that if f of x is a polynomial with degree n, and again, n has to be at least 1, so linear or higher, then there are exactly n complex zeros. So if we have a 4th degree polynomial, that means that we have 4 roots. Again, the roots could be imaginary or complex. They could be all real or they could be a combination. Also, some of the zeros may be repeated. Our non-real zeros, so if they're fully complex like that, they're always going to occur in what we call conjugate pairs. And conjugate pairs means that if you have a plus bi as a solution, then you also know that a minus bi is a solution. So the plus and the minus always come together in complex roots. So if I tell you that I know that 3 plus 2i is a root, then you also know that 3 minus 2i has to be a root. Let's look at an example. The number of roots for a polynomial function. Let's say that we have f of x is x to the 5th minus 7. How many roots are there? Well, what do you think? Their degree here is 5 because we have x to the 5th as our highest degree. So that means there have to be exactly 5 complex roots. Now this is going to bring us into a discussion about synthetic division. And I want to warn you, synthetic division looks really, really weird, and it can be really, really weird when you're first learning. But I promise you, it's just a set of rules and it's not overly complicated. You'll just want to practice these rules to get more comfortable with them. So we use synthetic division as a shortcut for dividing a polynomial, f of x, so any polynomial function, by a factor x minus a. We're going to end up with a remainder term, and if that remainder is 0, then we know that a is a 0, or x minus a is a factor for the equation, or for the polynomial. So I'm going to give you the steps for synthetic division, and again, they look a little overwhelming, but we're going to practice and you're going to see how it works. The first thing that you need to do is to arrange f of x in order of descending powers. Okay, so you want to start with your highest degree and work your way down. If a particular power is not there, then you need to use 0 as a placeholder. We're going to see an example of that. Now you want to write the coefficients for each power of x. You don't need the x's, you just need their coefficients. And for each column, you're going to add the terms in the columns that we're going to see to get the results. And then you're going to multiply a by the result of that column to move it to the next row in the next column. Your resulting numbers are going to be your quotient coefficients, and the last number is your remainder. Now, if you're utterly confused, that's totally fine. You probably should be. It's confusing just to explain it that way. But let's actually do it, and I think some of it will make more sense. Okay, so we want to use synthetic division to divide f of x is negative 10x squared plus 4 minus 2x plus x to the fourth by x plus 3. So the first thing we need to do is write f of x in order of descending powers. So x to the fourth is our highest, minus 10x squared, minus 2x plus 4. Notice here there's no x to the third term. There's no cubed term. We need to be sure that we use 0 as a placeholder, and we could rewrite it here as 0x cubed in there. Put it right where it belongs. We're dividing by x plus 3, and so if we have x minus a here, we know that a has to be negative 3 because x minus negative 3 will turn into x plus 3. Now we're ready to set up our synthetic division. Our coefficients go right here. So 1, 0, negative 10, negative 2, 4. And a goes right here. And I always draw these lines because that's just the way that I prefer to see it. Our first step is always to drop that first coefficient down. Okay, so nothing changes here. Our first coefficient drops down to be 3. Okay, always this, or to be 1 with a is negative 3. So our 1 drops down, stays 1, nothing changes. Now we're going to multiply that bottom number by a. So we're going to say here times here, and we're going to move that up. So negative 3 times 1 is negative 3. Then we add these two numbers, so 0 plus negative 3 gives us negative 3. And we're going to do that again. Negative 3 times negative 3 is going to give us 9. So we're going to write 9 right here. And when we write 9 right here, negative 10 plus 9 is going to give us negative 1. And we do it again. Negative 3 times negative 1 is positive 3. We write it right here. Negative 2 plus 3 is 1. We do it again. Negative 3 times 1 is negative 3. 4 plus negative 3 is 1. And this is our answer to synthetic division. We use those as our coefficients in our answer. So our quotient is at the bottom, and remember we're dividing by an x, so we're going to start 1 degree lower than what we started with. So we had x to the fourth here. So we're going to start with x to the third as our degree. These are our coefficients. So we have 1x to the third, negative 3x squared, negative 1x plus 1. And remember this last one is our remainder. So it is simply 1 over x minus a. Remainder is 1, x minus a is x plus 3. So if we divide our original f of x by x plus 3, this is what we get. Now, if our remainder is 0, then x minus, or x plus 3, excuse me, the 0 of a equals negative 3 is a perfect solution, okay? So that would mean that negative 3 would be a 0. But here our remainder is not 0. And so it doesn't go in there evenly. We know that x plus 3 is not a factor, not an even factor here. Now I want you to try. You're going to divide x cubed plus x minus 10 by x minus 2. Go ahead and pause your video, and you can press play when you're ready. Here's our solution. We have x minus a, so x minus 2. 2 is our a. Our coefficients are 1. We don't have an x squared term, so it's 0. 1 and negative 10. We move this 1 straight down to start. 2 times 1 is 2. 0 plus 2 is 2. 2 times 2 is 4. 1 plus 4 is 5. And 2 times 5 is 10. And negative 10 plus 10 is 0. Look at that. We have a remainder of 0. So that means that x minus 2 is a factor here. Our solution in polynomial form is going to drop down 1 degree, so 1x squared, or just x squared, plus 2x plus 5. That's our remainder. So now we know that the factors of this are x minus 2 and x squared plus 2x plus 5, and we could continue to factor further or use quadratic methods, whatever we needed to do to get what we needed. So what do we do now? Again, since our remainder is 0, we know that x minus 2 is a factor, which tells us that x equals 2 is a solution or a 0. If we looked at the graph, x equals 2 would be an intercept. We can write it as x minus 2 times our resulting quotient. This is really actually very helpful. Now we have one root here, and like I said, we can use quadratic methods or other factoring or whatever we need to use to get the solutions here. And we can easily get all three of our roots. Unfortunately, this piece doesn't look like it factors, at least not easily, right? So we have to use the quadratic formula. It came back to haunt us. Go ahead and give yourself a moment to try to solve for those roots. When you're ready, press play. So if we work this out, we know that we're looking for x squared plus 2x plus 5 equals 0. So our x coordinate is going to be given by that quadratic formula. And we see that -1 plus and minus 2i. So those are two roots. And the original x minus 2 is the other factor. So x equals 2 is one root. -1 plus 2i is another root. And -1 minus 2i is the last root. So we had a cubic function. So degree 3, and we had 1, 2, 3 roots, just as we would expect. Now, sometimes roots can be repeated, and that means that you have the same root to a multiple power. Okay, we call this a repeated 0, and we say that its power is multiplicity k. Usually when we're factoring or doing these, it's going to show up like x minus a to the k. We know that a is a 0 with a multiplicity of k. And something cool happens on these graphs. When it has an odd multiplicity, so if it's a single multiplicity, so it's not multiple, right? It's just one, or if it's 3 or 5 or any other odd power, you're going to have an actual x-intercept there that's going to cross through the x-axis, okay? It's going to actually cross the x-axis. But actually, if you have an even power, so you have x minus a squared or to the 4th or any other even power, it actually just touches, but it doesn't cross at x equals a. So it bounces off, or some people say it may kiss the axis, but it doesn't actually cross it. So let's look here at an example. We're going to use our graphing calculator and synthetic division to find all exact solutions to x cubed minus 8x squared plus 18x minus 11 equals 0. Now notice here, and it'll be the same on your test, you're finding the exact solutions. So you can't just use your calculator and take what it says for all of your intercepts, because some of them aren't going to be easy numbers. So you're going to need to use the quadratic formula or something like that to get your exact roots. Not to mention some of them may be complex, which aren't going to show up in your calculator at all. So the first thing that we want to do is graph this function in our calculator. Okay, so we're looking for these roots. If we look at the graph, we'll pretty easily see that 1, 0 is one of these intersections. It's one of these axis intercepts, okay? So an x-intercept at 1. These are not whole numbers, so they're not nearly as pretty, okay? So those we can't go with. But we can pretty easily see that 1 is a whole number, and it's there. And you could certainly use the 0 function in your calculator to be sure it was exactly 1 and not something like 0.97. So because we see 1, 0 as an intercept, we know that x minus 1 is a factor. Since x minus 1 would be a factor, that means x equals 1 is a solution. And now, since a equals 1 is a solution, we can use synthetic division to divide by that x minus 1 factor and see what's left. We also know that it actually goes through the intercept or through the axis here. It doesn't touch it and bounce back down. We're going to have an odd multiplicity, so 1, 3, or so on. In fact, it has to be 1 here because there are other intercepts. We know that x equals 1 is a root, so let's use synthetic division with a equals 1. And that'll give us our remaining coefficients if we divide by x minus 1. The 1 drops down as usual. 1 times 1 is 1, left with -7. 1 times -7 is -7. We're left with 11. 1 times 11 is 11. And look at that. We have a remainder of 0. If you've already looked and you see that a root exists, like we saw for the intercept at 1, 0, then you know that you should have a remainder of 0. If you don't have a remainder of 0, something's wrong. Either you didn't look at the graph properly or you didn't do your synthetic division properly. So now we're left with the factors x minus 1 times x squared minus 7x plus 11. Because remember, this is going to tell us x squared. This is minus 7x. And this is the constant of 11. We've now confirmed that x equals 1 is a root because this remainder is 0. So if I ask you on a test, hey, is x equals 1 a root of this? Then you can just go do synthetic division and see if the remainder is 0. Now to find the remaining roots, you're going to need to use the quadratic formula, because if you look here again, this doesn't factor. It's kind of ugly. You can pause this if you'd like some extra practice with the quadratic formula. But if we do this here, we see that we get 7 plus or minus square root of 5 over 2. We know that our roots are that original x equals 1. And then we know we have 7 plus the square root of 5 over 2 and 7 minus the square root of 5 over 2. We had a cubic. We had 3 roots. They're all real here, but they're ugly little numbers for 2 of them. Okay, now I want you to try. Let's find the roots for x cubed minus 9x squared plus 24x minus 16. The graph is here. When you're ready, go ahead. So we see that 4, 0 is an intercept. This is one of those kissing intercepts, actually. You can see how it touches right there and then it bounces back up. It doesn't actually cross it. So we know there's a multiplicity of 2 or 4 or whatever. It actually has to be 2 because we know it can't be 4 because there can't be more than 3 zeros. So since we know that x minus 4 is a factor, and it has to be a factor twice, then we can actually divide with synthetic division by x minus 4 twice. So divide this by x minus 4 with synthetic division, and then divide that result by x minus 4. And then you'll be left with all the answers you need. So the first time we do it, we're going to have 4. These are our coefficients. Okay. The 1 moves down. We go through synthetic as usual. We get a remainder of 0, which is good because we knew the remainder should be 0. So this leaves us, we started with a cubic, so we go down to a quadratic, degree 2, x squared minus 5x plus 4. Okay, so if we do it again, we divide by x minus 4 again on this polynomial. So we're left with 1, -5, and 4. We do it again, and now we see that this result is x minus 1. So now we can say, well, we know our factors are x minus 1, x minus 4, and x minus 4. Now you may have noticed that you could factor this right here, but we're trying to demonstrate that doing it multiple times is a good idea. Several ways to get here, okay? Just as we expected, we have a multiplicity 2 here because it kissed right at x equals 4. So how do you even know where to start? There's a lot of information here. Well, often you can look at the graph to get an idea of your exact roots. If you look at your graph and there's a whole number intercept, awesome, start there, then work from synthetic division. It gets really complicated really fast if it's not a simple fraction, okay, or a whole number. Honestly, even simple fractions can get fairly complicated. To help us, if we don't have any other options, we can use something called the rational solutions test to help. So remember that a rational number is anything that can be written as a fraction, okay? A and B have to be integers, so we don't have square roots in them. We have integers. So excuse me. The rational solutions test tells us that if we have a polynomial here in order, degree n all the way down to our constant term, and the coefficients are integers, so no fractions for A, then the rational roots have to be of the form P over Q or negative P over Q, where P is a positive factor of your constant term and Q is a positive factor of your leading coefficient. So all potential roots can be listed. Doesn't mean that they are all roots. That means they're all potential roots. So you're going to list the factors of this and divide by the factors of this and have the plus and the minus versions. Let's look at an example. We have 2x cubed plus 7x squared plus 5x plus 1. So here we have 1. The only factors of 1 are 1 and 1, right? And we have 2, and the only factors there are 1 and 2. So we can have 1 over 1, negative 1 over 1, 1 over 2, or negative 1 over 2. Okay? So those are all 4 of our possible roots. Now, what do you think we do now? We can test to see if these are valid roots by going ahead and doing synthetic division with each. If we do the synthetic division and it has a remainder other than 0, then it's not a root. If we have a remainder of 0, then it is a root. So let's look. This is a great place to pause and get some practice with synthetic division. If we use 1, 2, 7, 5, and 1 are our coefficients, and we do synthetic division, and we see that our remainder is 15. That's not 0. If we do the same thing but with negative 1, we get a remainder of 1. Again, not 0. I highly encourage you to pause this and make sure you get some practice with synthetic division here. Now, if we try 1/2, now we get 11 halves. That's still not 0. And finally, negative 1/2 is going to give us a remainder of 0. Finally, right? Happened to be the last one that we tried, the last possible one, right? We got very unlucky here. Unfortunately, there's no good trick. Sometimes it'll be the first one you try, sometimes it'll be the last one you try. It's just hard to know. A lot of times it's based in trial and error. I would encourage you to use a calculator graphing view to get an idea of the possibilities. If you look at the graph and there's nothing near 1 or negative 1, then don't try those first, right? If you see something that's maybe near 1/2 or negative 1/2, try one of those first. So now we know that 1/2, negative 1/2 is a factor. So x minus negative 1/2 is a factor. So that turns into x plus 1/2. And if we use the coefficients from that synthetic division, we get this remaining polynomial. Since it's x squared, we can just use the quadratic formula to easily get our remaining roots. And we do that, we get negative 3 plus or minus the square root of 5 over 2. So our roots are negative 1/2, negative 3 plus square root of 5 over 2, and negative 3 minus square root of 5 all over 2. Great place to practice. Now, rational solutions test sucks, okay? Obviously. You can see that other one, we only had 1 and 1 for potential factors for the constant term, and we had 1 and 2 for the leading coefficient, and we still have 4 things to test. You can see if you had larger numbers that had more factors, that could get really ugly really fast. So we don't always need to use the rational solutions test. It's just a tool in our toolbox, okay? Honestly, I use it as a last resort. If we have other methods available, we want to use them. But again, sometimes the calculator isn't very helpful, okay? So this is a nice flow chart that can help us decide what to do. First, look at the polynomial. Is it quadratic? Because if it's quadratic, use the quadratic formula or some other quadratic method that we've learned. If it's not quadratic, then think about, do we know any of the zeros? If we know a 0, use synthetic division, and then you have your remaining polynomial. Then you can go through with that and go back and find those zeros. If you don't know anything about the zeros, look at the graph or try to factor. If you can look at the graph or factor, you can save yourself a lot of heartache. When you know that if you look at the graph, you can use synthetic division, okay? If you factored, you might have that factor straight away. But you're probably going to need to use synthetic division to get your new polynomial. If you still can't do anything with the graph or any other helpful way, use your rational solutions test to list your roots and then try synthetic division one by one by one until you find a remainder that is 0. Then you get to repeat all of that fun with your new remaining polynomial until you get a quadratic, and then you can go that route. So, for example, let's say that we're asked to find all zeros of this polynomial function. We don't have any zeros right away, right? We're not told anything about the zeros. If we look at the graph, which I don't think I've shown here, there are no easy answers. Go ahead and graph it in your calculator and you'll see like, oh crap, there's nothing really helpful there. It's not quadratic because it's cubic and we can't factor anything out. So this is a good place to start with the rational solutions test. Again, we'll find one root and we'll use the quadratic methods from there. So looking back here, we see our factors are 7 and 1 for the leading or for the constant term. Our leading coefficient has 7 and 1 as its factors also. And so we're going to look at all possible combinations of 7 and 1 and plus and minus. So that means that we can look at plus and minus 1, plus and minus 7, and plus and minus 1 over 7. That's 6 possible options right there. If we test with synthetic division, give yourself some practice, you'll see that negative 1/7 works. And with our synthetic division, we get 7x squared plus 35x plus 49 as our result. Then we use the quadratic formula. We're not going to use rational roots again. Use quadratic formula again to get these roots. Okay? And you'll actually see that 2 of these roots have imaginary components. They're fully complex. So this was a very heavy section. I fully recognize that. Okay? Get some practice, it gets easier. Remember, there are some key easy take-home pieces here. If you have a polynomial of degree n, then you know that there are n roots. The roots may be real, they may be imaginary, or they may be complex with components of both. Okay. You can also have repeated roots that count for multiple zeros. If you don't have any help with the graph or factoring or any other method that we've already used, the rational solutions test can help you get started. Okay, you have to use synthetic division, but it can help you get started. Definitely get some practice here. And you'll be able to know kind of what you need to know based on your homework and based on the practice test as far as what we'll be asking. Again, this section is very important if you're going to continue on to calculus. It's good to know even if you're not going to continue to calculus, at least through the rest of this class. You guys are almost there. And there's only one more section that I'm going to talk about. I hope you'll tune in. As always, thanks for listening and have a great day.